Today we're going to look at applications, well, geometric problems. And again, some of these are very, very simple, and so we actually skip them. Things like computing projections of a point onto a convex set, doing things like calculating distance between two convex sets. These are just too simple to even mention. So we're going to skip those, although they're kind of obvious by now. An example of that would be, how do you compute the distance between two polyhedra, right? So without even writing it down, you should know by now, that's just a QP. You minimize norm x minus y, 2 norm, subject to ax less than b, and fz less than g. Okay, so we don't cover that kind of stuff because it's too simple. Instead, we're going to focus on stuff that's less obvious and really, quite interesting and very useful. So the first topic is going to be the Lohner-John ellipsoid. And this is not obvious, although these things have been known for about 100 years, although nothing was known about it computationally, right? This was not an algorithmic thing. This was just theory until maybe 20 years ago. So basic idea is you want to compute the minimum volume ellipsoid that covers a set. And it's completely general. So I have a set, C, and what I want to do is compute the minimum volume ellipsoid that covers it. So that's the idea. By the way, there's tons of applications of this, right? One would be to give a C could be very large, very complex, and instead all you want is sort of a summary of C that is smaller, right? And so to describe an ellipsoid takes on the order of n squared, in fact n squared over 2 parameters to describe an ellipsoid in Rn. So that's sort of a compact way to do this. And this approximation covering a bunch of, when you're covering a bunch of points, it's a conservative one, I guess. So you'd say that you're going to cover more than just the points. So, all right. Now, generically, you can solve this problem. I should be more careful about it. We can generically write this as a convex optimization problem. So computing the minimum volume ellipsoid. But there's going to be an expression that comes up in the constraints that may be handleable. It depends on that being tractable before this becomes a tractable convex program, right? Oh, and I guess we're far enough along in the class that it's time for you to, we can actually be more honest here and admit things like there are non-tractable convex optimization problems. This is kind of obvious, right? Because if I write a convex optimization problem, but for example, to evaluate the objective or a constraint function is itself intractable, then you're in trouble, right? So, okay. So what we'll do is there's a very carefully chosen parameterization of the ellipsoid, and we're going to write it as this. It's the inverse image of the unit ball under an affine mapping, right? So we're going to take the ellipsoid E to be the set of points for which the 2 norm of AV plus B is less than 1, right? So that's the inverse image of the unit ball under the affine mapping AV plus B, okay? Now, here, of course, A could be anything. I mean, it has to be square. Well, it wouldn't even have to be square. But we can, without loss of generality, we're going to take A to be symmetric positive definite. Okay. Now, the argument there, I'm just going to go over it very briefly here. So this is going to be a little obscure, but hopefully you can follow. The argument is this. Here, I can multiply A and B on the left by any orthogonal matrix, and it will define the same ellipsoid. Everyone agree with that? Because it doesn't change the norm. But if that's the case, I can take an arbitrary non-singular matrix, multiply on the left by an appropriate orthogonal matrix, and make it symmetric positive definite, right? And the way you do that, again, I'll just talk through it because it's, I don't know, we're far enough along that we can do this. We can go faster. You just take the singular value decomposition of A. So you have U sigma V transpose, and you multiply on the left by V U transpose. And that's an orthogonal matrix, and it converts it to symmetric positive definite. Okay? So that's the idea. Now, the volume of this ellipsoid is proportional to the determinant of A inverse. In fact, the constant of proportionality is exactly the volume of the unit ball in Rn, right? Which actually doesn't, if we're minimizing, it hardly matters what that is. It's something, it's got some pi's in it and some gamma functions or factorials and things like that, but it doesn't really matter. So it's proportional to the determinant of A inverse, right? Because when things map under affine mappings or linear mapping, affine mappings, volumes transforms like determinants, okay? So All right. So now our problem looks like this. It says minimize over variables a and b, log det A inverse, right? So that's the log of the volume, well, up to a constant, right? Because it's an additive thing. Subject to the condition that every point C is in this set. And one way to say that is that for every point in C, the norm of AV plus B is less than 1, right? So you could write this way, or you could write it as, I could remove the soup and say for all V and C, okay? And that would be the condition, right? So that's the condition. You might ask, why does it say in parentheses here over AB? Because this kind of problem generically ends up with maximally confusing notation. And then, of course, norm of linear is convex. And this is true for any V. So supremum, that's pointwise supremum, that's convex. So, okay, so here, that's a convex optimization problem, and it computes the minimum volume ellipsoid that covers a set C. Now, the question is whether it's tractable or not, and it's tractable precisely when this constraint is handleable, right? So here's a simple case where it is. There's actually a whole bunch where it is. I mean, not a whole bunch, but there's a bunch of cases where it's tractable. But here's one where it is. Let's look at this. Let's take C to be a finite set. So I have a cloud of points, and I want to compute the minimum volume ellipsoid that covers it, right? So that's the idea. So here, well, that's very simple because the sup V and C is nothing but it requires that each of these points is in the set, and so you get this. And of course, that's the Lohner-John ellipsoid for a polyhedron described by its vertices, right? So what that says is, if I give you a bunch of points like this, and then you calculate, then you take the convex hull, right? Then computing the minimum volume ellipsoid that covers that is an entirely tractable convex problem. Okay? So, by the way, these things are not obvious here. So, for example, if I could give you an ellipsoid described as, a polyhedron described as the convex hull of a set of points, and as I could give you vertices. And I could ask, find me the maximum volume ellipsoid that lies inside it. That's another natural problem that we'll look at shortly. That's actually NP hard. Okay? So these things are, I mean, you really have to be very careful with these things, right? That depends on the description, and it depends, whether it's extremely easy or extremely hard depends on the description. Okay, so that's the Lohner-John ellipsoid. Well, the dual, roughly, of that is the maximum volume inscribed ellipsoid. So here we have this time the set has to be convex. I mean, it doesn't have to be convex, but then it's actually quite intractable, right? So we take a convex set, and then the idea is we want to find the maximum volume ellipsoid that sits inside it, okay? And we do that this way. This time, we're going to parameterize the ellipsoid as the forward image as opposed to the inverse image of a unit ball under an affine mapping. So here, it's the set of points BU plus D, where U is in a unit ball, right? So, by the way, there are lots of different parameterizations of ellipsoids, and it's generally linear algebra that would go between the different canonical representations, right? It would be elementary linear algebra, like, square roots of matrices, things like that. What's interesting is they all have different convexity properties, right? So a problem would be convex in one, but not the other. So whenever you have problems when you optimize over ellipsoids, they're actually kind of fun because it's not like a problem where something's just given to you on a platter. You have to figure out the appropriate representation to make it convex, if that even exists, right? So, okay, so here's the forward image. And in this case, the volume is proportional to the determinant. We want to maximize it, so we maximize log determinant, right, which you recognize as tractable because log determinant is concave. And here, the condition is this. This condition right here is simply this, right? So this condition here says that if you take the unit ball and you multiply B by it, add D, that this set lies entirely in C. So that looks like this, right? I mean, this is just a long and complicated way to say that for all u of norm less than 1, bu plus d is in C, right? I guess it's written this way so that we can verify instantly that this is convex, right? And the way to do that is very simple. This thing, that expression, is linear in the variables, which are b and d. IC, that's the indicator function, that's of course convex. So that's convex. So for each u, this is convex. That's a supremum of convex functions, so that means that the left-hand side is convex. So you have a convex inequality. Okay, so again, once again, the issue is the following. Is evaluating that function tractable, right? And there's very simple cases where it's not. Here's one. If I simply give you a finite number of points and I ask you, does that hold there? That's actually, that one is actually going to be NP hard, right? Not a finite number of points, sorry. The convex hull of a finite number of points, that's actually NP hard, right? So it's sometimes tractable, sometimes it's not. But here, and there's a kind of a pretty duality here. What's interesting is it turns out, remember that computing the minimum volume ellipsoid is tractable. The canonical case is when you give the vertices. So computing the maximum volume ellipsoid is tractable. And again, almost aesthetics almost requires this, right? Because just to make it pretty. It's the dual representation of an of a polyhedron, which is in fact given by its linear inequalities, right? So what happens is here, if I give you a polyhedron defined by linear inequalities, then this is really simple because basically you're asking, when is it true that AI transpose times BU plus D is less than BI for all U less than 1, right? That's the question. What are the conditions on B and D under which this holds, right? And this is actually relatively easy to work out, right? So you have AI transpose D, that comes out fine. And then here, you need to calculate, what's the largest possible value of that? But that's easy. That's the converse Cauchy-Schwarz inequality, right? Because it says you have something which is BAI, and then you take an inner product of BAI with a vector u whose norm is less than 1, and you want to know the maximum value of that, and the answer is the norm of BAI, right? That's Cauchy-Schwarz, or the converse of Cauchy-Schwarz, okay? So this problem translates to this. That is, again, you have to be on your toes here because the variables are B and D, which parameterize the ellipsoid here. And that otherwise these are just completely legitimate constraints. That's clearly a concave function that you're maximizing. And the inequality here, again with B and D, that's a linear term here. That's linear in B, right? And so that norm term. So these are second order constraints. So there's actually some very interesting things you can show about these ellipsoidal approximations. So let's take a convex, bounded, non-empty interior set. And it's the following, that there's actually this basic efficiency. It says that if you take a set, so here's a polyhedron given by its vertices. This is the Lohner-John ellipsoid, the minimum volume ellipsoid that covers it. It says if you take that Lohner-John ellipsoid and you shrink it by a factor of n, that's the space dimension, right, about its center, that's guaranteed to be inside the set. Okay? Everybody got that? And so actually what that says is that you can, I'm going to say it something like this. It says that any convex set in Rn can be approximated within a factor, in fact here I'll even try it this way, can be approximated within a factor of square root n by an ellipsoid. Everybody got that? Now, I mean, you might not like the factor square root n, but the point is, that's what that says. Everybody, and by the way, that statement is completely false. I mean, you can talk about things like with other classes of geometric objects, right? You could talk about things like a bounding box, right? And it's just completely false, right? All sorts of other things you might imagine, things, data structures to describe regions in Rn, and it's just not the case. I mean, there are others, right? One would be like a simplex, right? So that's another one. Now, by the way, in this example, you can see that factor of 2, I mean, this is in space dimension 2, right? In here, you can see the factor of 2 was not needed. It's quite likely, I mean, in this case, take a look at it. Here, I mean, we can eyeball it, okay? Probably you didn't have to divide by a factor of 2, but you just divide it by like 20, 30%, and you're inside, okay? And by the way, That factor is an interesting number. You might call that, how ellipsoidally approximable the set is or something. I don't know. So, hey, everybody see what I'm saying here? So it just guarantees. By the way, what's the worst possible set to approximate by an ellipsoid? What is the convex set that is the worst possible one? Simplex, there we go. Okay, so let's do triangle like this. There's your minimum volume ellipsoid's a circle. There it is. And in this case, guess what? You have to shrink it exactly by a factor of n before it fits inside. And that tells you that this factor of n cannot be improved. Okay? So the least ellipsoidally approximable convex set is a simplex. I've drawn it this way, but in fact, all of these ellipsoid approximation methods, they're actually invariant under affine transformations, right? Because if I take a set, if I multiply it, if I apply an affine transformation, what'll happen is volume transforms under affine transformation just by a determinant, by a constant. So you get a commutative diagram. In other words, if you take the original set, affine transformation, optimal ellipsoid, then apply an affine transformation of the optimal ellipsoid, you get the optimal ellipsoid for the second case. You get a commutative diagram. Okay, so in other words, you might say something like this. Extremal volume ellipsoidal approximation is affinely invariant. Everybody got that? That's actually quite important. Actually, it's quite important in practice, right? Because it says that if the x's represent things and you actually don't have any idea how the scales should go together, I mean, if it means nothing to you, then there are plenty of cases like that, then it says you should probably, whatever your method is, should be affinely invariant. So, I should say something like this. If the polyhedron is symmetric, symmetric means if x is in the set, so is minus x, right? So an example would be a norm ball. Then it says this factor is not n but square root n. Okay? And I said something obscure at first. I said any convex set can be approximated by an ellipsoid within a factor square root n, right? And so let me explain what I was saying. That's kind of, I take the minimum volume one and I divide it by square root n, right? So I put the one that's geometrically in the middle. And what that means is for any convex set, I can produce a convex set which has the property that if I expand it square root n, I cover, and if I shrink it square root n, I'm inside. Okay? So actually, philosophically, it's quite interesting. It's you can argue something like this. Ellipsoids are universal approximators of convex sets. Yeah, I mean, square root n is not a fantastic. By the way, it's the fourth root of n for symmetric, right? You might not like that, but the point is it's a constant, right? And that's it. I mean, it's even a constant that doesn't grow that badly and all that kind of stuff. So this is actually interesting, and it kind of explains a lot about why things like quadratic methods would be so prevalent. By the way, one interesting thing you can say here is the following. Any norm on Rn can be approximated by a quadratic norm within a factor of n to the 1/4. Okay? And that's interesting, right? Because it says that any norm, and there are some very sophisticated norms, right? It says that every single one is approximable within n to the 1/4 by a quadratic one, right? So that tells you actually, I think to me this is sort of a philosophical, this explains why using least squares for the last 2 centuries, people have gotten pretty far, right? This at least explains it. Next topic is centering. So, I mean, and here there's tons and tons of applications of centering. I'll just address that first. You've seen a couple already. Even in the first couple of weeks, we saw yield maximization. So yield maximization says that you're running a manufacturing process. You want to tell your machine to target a certain set of critical dimensions, let's say an IC manufacturer. But since you're pushing it, right, you're pushing it absolutely to the limit of the technology. When you say, please make this critical dimension 1 nanometer, it's going to be off a little bit and things like that. So there's variations. And so there you have a polyhedron that describes the acceptable critical pairs, combinations of critical dimensions. And what you want is you want to tell them the target you want to shoot for is something deep in that set, so that when you have variations away from it, you're still in it. Your yield is high. Okay, so we looked at all that. So that comes up, and we've even seen some of these problems. So here's one: find the center of the largest inscribed ball. That's the Chebyshev center, and that's this problem. I give you a polyhedron described by inequalities, and I say, please find me the ball of maximum radius that fits inside, and the center of that we're going to call the Chebyshev center, and it's the point deepest in the polyhedron, right? And that's means, well, it's clearly defined, right? It's the one which has highest depth, highest distance to the exterior, right? That's this, and that's an LP. That was actually one of our first examples when we looked at LP, and it was a fun example because it doesn't look like it should be an LP, right? Because, well, it looks like an LP while you're drawing the polyhedron outside, but the minute you draw a ball, that should, that should not evoke LP, right? But it's an LP. Okay. A more sophisticated one is the center of the maximum volume ellipsoid. Actually, that's quite interesting because this one is actually invariant under affine coordinate transformations, right? Now, that may not be relevant to you, right? If your coordinates are things you know about, you're intimately familiar with them, and you really do know the range of each one, and they all have separate meanings, good for you. And affine invariance doesn't mean anything, right? But in a lot of cases, that's just not true, right? That these are sort of arbitrary coordinates. These might be features or something like that, and you don't know the scale or anything, right? You pick a reasonable scale, and that's about all you can do. Okay, so this is one. This is the center of the maximum volume ellipsoid. There's one that we are going to be looking at very much in the next couple of weeks. We'll see this. I mean, it'll take a while, but maybe in 3 weeks, 2.5 weeks. And that's the analytic center. So this is a good time to look at it. So the analytic center is actually not a function of the set. It's actually a function of the description of the set. So technically, I don't know, it's not the same as the minimum volume ellipsoid and all that kind of stuff. So here's what it is. Suppose I have a set of convex inequalities and equalities. Then I simply form the following problem. I minimize the sum of the logs of the minus FIs. The FIs, of course, minus FI, well, it has a perfect interpretation. It's the margin in the ith inequality, right? Because the third inequality says F3 has to be negative, less than or equal to 0, right? So if F3 is minus 2.1, you have a margin of 2.1. So these are the margins here, right? Positive means you're in the interior of the set. Well, relative interior because of this, okay? So here, this is the log. It's the sum of the logs of the margins. Well, it's the product of the margins, right? So this says maximize the product of the margins. That's what this is, okay? So it says, and this comes up in a lot of things. That's a convex optimization problem, of course, right? Because minus log minus arg is a convex increasing function, right? I mean, you have to trace through the two minuses to see what happens, right? The first minus changes the sign, the monotonicity, and it changes concave to convex. And the second one flips the monotonicity, okay? So, or makes it go back to be increasing, right? So by the composition rule, this is a convex function here. And that's called this function is called the log barrier, right? So it's a barrier function, right? And the meaning of that is that on the set of points where this is strictly less than 0, this thing's finite. As you move that point towards any point where one of these goes to 0, one of these margins goes to 0, and the product goes to infinity, right? Well, the sum of the negative log margins goes to infinity, right? So this actually is extremely easy to solve. I mean, it depends on it depends how f is given, but we'll see that later. But it's not a property of the feasible set. It's actually it's a function of the description of the problem, and that'll be clear in a minute. But for fun, let's just look at the analytic center of a set of linear inequalities. So here's a set of linear inequalities like this, and what's plotted here are various things. These dashed curves show the level sets of the log. This is the log barrier. And what are showing here are the level sets of the log barrier, right? So actually, if you say, what's the level sets, where are they equal to, where is it equal to 1,000? You get a kind of a cool little, curve, a smooth curve here, which hugs the boundary of this thing very closely, right? And then as I decrease that number, this number is 1, by the way. When I decrease that number to 1, it's looking more ellipsoidal. It's not. And as I keep going lower and lower, and actually the Hessian of this thing at the analytic center is actually a good ellipse quadratic summary of the shape of this set, right? So that's a good way to do that, right? So actually, in a lot of cases where you know how to do something if you had a quadratic representation or something like that. We'll see optimization methods where this is the case, or statistical methods where this is the case. But you don't have anything like that, which has a complicated convex set. One option is to do something like this. I mean, another option, of course, is calculate maximum volume ellipsoid inside it and so on. Okay. Now, it turns out here there are guaranteed approximations, right? So one is this. It turns out that if you form the following, so the inner ellipsoid is, you go to the center and you take the ellipsoid defined by the Hessian of the analytic center, that actually, with a 1 here, that always lies inside the set, and this one always lies outside the set, covers the set. This is a worse approximation ratio than the maximum volume one, right? And the reason is this. This number here is m, let's call it m squared. You take the square root and that gives you the expansion size, right? So it says that if you, it says this. It says if you take this thing here, that's shown in dark, is shaded here, that ellipsoid is inside the set, and if I expand it by a factor m, which is, by the way, not the ambient space dimension, it's actually the number of inequalities, but the number of inequalities is at least n plus 1, because it takes n plus 1 inequalities in Rn to get a bounded region, and if you have n plus 1, you have a simplex, right? So that's the, so this is a worse approximation ratio. So, it's not clear that matters, right? One question here. Here I have, let's see, 1, 2, 3, I have 6 inequalities. But analytic center is not a function of set, it's a function of the inequalities. What if I added a new inequality that looked like that? So it says, please stay on this side of that inequality. Yeah, it shifts left, exactly, right? And in fact, the following is true. Given a polyhedron, or actually just for that matter, just given a set, I can take any point in the interior and pile up a bunch of, this is you could call that a redundant or irrelevant inequality, right? It doesn't change the set. So I can pile up redundant inequalities, and I can get any point in the interior to be the analytic center, right? So all that says is analytic center is an attribute of the description of the set, not the set itself. Okay? So technically it's not a question of geometry, right? It has to do with the description. Okay. Another topic is linear discrimination. So, and if you've had a course on sort of machine learning or something like that, or modern statistics, you've seen things like this. So, here's the problem. This is actually also quite an old problem. I think it goes back at least to the 40s, something like that. I don't know how old the perceptron algorithm is, but so you have a set of points, x1 through xn, y1 through ym, and in some Rn. And the idea is to determine whether you can separate them by a hyperplane, and if so, find such a hyperplane, right? And there's actually a few tricks here you want to watch very carefully in the next few minutes, because you will be doing these things yourself. And the arguments are, they're not totally subtle, but you have to listen. All I'm saying is you better listen, okay? That's the right way to do it. So here, and I'll go over it a bit slowly. So what it is you really want to know whether or not this set of inequalities is feasible. Now, the first thing you notice about those inequalities is they're strict. And you might say, hey, wait a minute. We've been doing this class for a long time. We haven't seen strict inequalities before, right? And then you might say something like this. You might think about it for a minute. And it would generally be true. The following would be true. if your problem, if the difference between a strict inequality and a non-strict inequality, like, changes your problem, that's kind of a mathematical pathology, right? You know what I'm saying, right? If you say, hey, I just built I just built a machine that gives, the correct dose on a tumor or something like that, and I can satisfy these inequalities. And someone says, oh, what are they? Which inequalities can you use? You say, I can do the non-strict one. You go, no, no, it has to be strict. I mean, it just makes absolutely no sense. No sense whatsoever, right? Because the difference between the two is, I mean, it can hardly matter that if it turns out the difference between putting 49.999 grays on some on some tumor voxel and 50, if that really makes a difference, then give up and go home, because this doesn't make any sense. This is not the real world, right? Or that would be something like in at a hedge fund. You come back and you go, oh, great news! I can get this return with this risk level, and they go, equal to the risk level or less than? I mean, the answer is your risk model is so ridiculous, it's just totally made up. So the point is, if somebody is telling you there's a difference between strict inequality and non-strict inequality, it just makes no sense. Everybody following this? Okay, right. So let's apply that common sense principle here. Let's take this and go like this, like that. Okay, there you go. Now you tell me. Now the good news is the problem has become actually substantially easier. So the answer is A equals B equals 0 is feasible. Okay, everybody got that? Okay, all right. So that didn't. So the standard method, right, didn't work here. Okay, so that means that the common method doesn't work. Okay, so let's do something. Here you have to be a bit more subtle. What you do is you observe that these inequalities are homogeneous in A and B. Okay, so that's, in other words, if there's A and B for which AI transpose X plus B is positive, then I guarantee you there's A and B for which A transpose X plus B is bigger than equal to, is bigger than equal to 1. Okay? Why? I mean, you just scale them all up until it's true, right? So what it says is we replace this with this. And I would strongly recommend that you go to a quiet place and make sure you understand exactly the semantics of what went down there, right? Right. It is not the same as saying that a strict inequality is always the same as replacing with 1, right? So you have to make the observation that these are homogeneous, that I can scale them, and then they become equivalent. Okay, that's the idea. This is a bona fide set of linear inequalities. In fact, that's a linear program in A and B, right? So interestingly, questions about linear discrimination, it took unfortunately a shock and a much longer time than it should have for somebody to look up one day and say, oh, hey, that's a linear program, right? So sadly, historically, but it really did. In fact, whole algorithms were worked out to solve these kinds of things before it was understood that other people had worked out other whole algorithms to solve these kinds of things, and so on and so forth. I mean, now I think there's even a legacy of that in current machine learning. I mean, there's some weird. Anyway, maybe I won't go. I won't go any farther. But okay. All right. So what does this say? This says that if I give you a bunch of points, pairs of points, and these might be like labels or something like that, then it says I can now, by solving an LP, I can determine if they are, you would say, linearly separable or linearly discriminable, right? So you could test, and if they are, you can exhibit or deduce the separating hyperplane. Now you can optimize over that hyperplane. We're going to see that next, right? Like you could, find the smallest one, or we'll see all sorts of things you could optimize now, right? And what would be the idea behind this? Well, it might be something like this. This is a giant pile of data here. In fact, you'd call this, you'd say labels, right? So these would be feature vectors, right? So this is, I look at, let's say, 1 billion emails, right? Each one is labeled as either spam and not spam, right? So that's, I don't know, that's spam, that's not spam, okay? And how do I know that? Because I watched when someone junked something or something like that. So I got a pretty good idea of the labels. And let's say each of these is I have a feature that's, let's say, I'll be safe here. Let's make it just like 5,000, 10,000 features, right? For each email. And they could be, a lot of these features are kind of obvious that they're what you think they would be. That'd be things like word counts and things like that. All right, so you take a billion of these points, some x's, some y's, right? And then you'd want to know in R1000 or 10,000, whatever however many features we decided there were, you'd like to know if there was a hyperplane in between them. And if there were a hyperplane, then it'd be easy, because now you take that hyperplane, a new email comes in, you compute its feature vector, find out which side of the hyperplane you're on, and either announce it's spam or not. And in fact, even the distance of the hyperplane would tell you something. Like if it was way off on one side, you might say with high confidence that it is spam or not. Everybody got this? Okay. Now, actually, you would be quite nervous if in fact it's separated, right? It'd be something deeply wrong in this case. But at least that's abstractly the idea of the use of these types of things, right? So, okay, we will get to that. So it turns out actually a very simple variation on this produces something that's actually extremely effective, right? So, okay, so the first thing we're going to look at is this. If you have a set of linear inequalities, right, that just detects a hyperplane, but the point is there's lots of hyperplanes that separate two clouds of points if they're separable. If they're linearly discriminable, there's lots of hyperplanes. So, by the way, there's lots of ways you could choose a hyperplane that separates them, right? There are lots of reasonable ways to do it. One way would be to do some kind of robustness thing. And one would do that. What you would do something like this. You can imagine the hyperplane is A transpose Z plus B is 0, right? But instead, what we could do is we could take the points where that's 1 and minus 1, and everything in between those two parallel hyperplanes, that's a slab, right? And then we could very reasonably ask to compute the maximum width slab that separates the 2 points, right? And by the way, what's nice about that, I mean, some people would call this like a maximum margin classifier, right? And the reason it's maximum margin is that you can puff up each of these points by a ball, still classify correctly, and the amount you could puff them up by is the largest possible, and still maintain correctness. Everybody got that? So it's maximum margin classifier, I think. Okay. Completely reasonable, right? But the width of this slab is exactly 2 over the norm of A, right? So that's the, right? I mean, if the norm of A were 1, then, well, A transpose X plus B literally is the signed distance to the hyperplane, if the norm of A is 1. If norm of A is big, then, in fact, this slab is small, right? So, okay. So then it says, please, let's maximize 2 over the norm of A2. That's the same as minimizing norm A2. And so you'd say minimize the norm of A2 subject to these inequalities. And now we get a QP. And that's the maximum margin classifier, if I'm saying that correctly in whatever dialect that is. Oh, and I guess they would do this, because it's not, yeah, you'd have to square the objective. You'd do something like that, right? It'd be the same thing. Okay. Okay, so now if two sets are separable, linearly separable, we at least have a very nice, an utterly reasonable way to find a hyperplane that separates them. It's kind of like it clearly has some good properties. Okay. Very interesting thing is to look at the dual of this, and we'll do that quickly. So I just mechanically worked out the dual of the separation problem. So the dual of this problem, right? This maximum margin problem is exactly this. It's maximize this function subject to, and here what you see is something very interesting. I get two sets of Lagrange multipliers, lambda and mu. They are associated exactly with the two sets of linear inequalities, right? For the x's and for the y's, I have these kind of inequalities go the wrong way. And you get some very interesting constraints. I get a norm constraint here. These are, well, those are inequalities, so these things are non-negative. And I get this equality constraint here. So again, everything is homogeneous here. So what we're going to do is the following, is I'm going to normalize these things here to be, I'll take both of these to be 1, whereupon lambda and mu become, well, they're probability distributions, or they are, I don't know, they're convex mixtures, right? They're numbers that are non-negative and add up to 1. But if these are numbers that add up non-negative and add up to 1, these two things are really simple. They are arbitrary elements in the convex hull of the x point cloud and the y point cloud, right? And so that says I can rewrite the problem to look like this, and it's really beautiful. It basically says take the convex hull of the x point cloud, convex hull of the y point cloud, and actually calculate, that's an arbitrary point in one, arbitrary point in the other, and it says, this is the epigraph, I mean minimizing t subject to the same as you just minimize this thing here. It actually says find the minimum distance between two polyhedra described by their vertices. Everybody got that? So that was it. It makes perfect sense. So now you know when are two point clouds separable, linearly separable. The answer is if and only if, and straight from duality is this. It's if and only if the convex hulls don't intersect. That's it. Okay? So and that's duality, right? That's exactly what duality is. Okay? Everybody, this doesn't say anything, but it's just fun to look at, right? So, okay. Now we're going to get to a real case, and in fact, it's one of those things where you just add one more feature to the problem, and then it goes from being maybe not so useful to off-scale, unbelievably useful. Okay, so those who've taken a modern statistics or machine learning course know what's going to happen now. So, but anyway, so if you just sit tight, everything will be fine. All right. So what you do is this, and in fact, I wanted before we even get into this, I want to talk about. Let's start the story this way. I give you some x's and I give you some y's. These are feature vectors for spam and for not spam. You calculate whether there's a separating hyperplane, and there isn't. Right? And that's probably good, right? So, oh, by the way, if the 2 point clouds are like totally, if they're totally on top of each other, so there's no difference, that's not good. That means you've picked some pretty poor features, okay? Right? But so the point is that 2 point clouds are there. They do the two convex hulls intersect, period. In other words, there are spam feature vectors that penetrate into whatever the non-spam territory. Everybody, I mean, this is just a picture. Okay. And so the question is, how would you, let's skip what I have on the slide here. What would you imagine you might want to do? So you have a million linear inequalities you want to satisfy, and they're not mutually satisfiable. Yeah, so I have a whole bunch of inequalities I want to satisfy. I solve an LP, and I announce with total confidence, there is no hyperplane. I cannot satisfy all these inequalities. It's impossible. So I think one of the most natural things you might want to do next would be to say, okay, fine. Find me a hyperplane that minimizes the number of inequalities you violate. Now, if you want to think about a classification problem, that's the number of misclassifications, right? And by the way, if that number were like 0.5%, you'd be very happy. You wouldn't, but okay. At some point in time in the past for spam detection, you would have been very happy. Right? For a lot of problems, you'd be delighted, right? Everybody see what I'm saying? So then the problem is to figure out which ones can you not, how do you minimize the number? Okay, well, by the way, then you might ask yourself, what kind of an optimization problem is that? And you would find out pretty quickly that that is NP hard. So I give you a set of inequalities, and I ask you to satisfy as many as you can. It's NP hard, okay? Fine. Okay, so then you'd say, well, let's see, maybe there's a heuristic for this. And what does this mean? This means that the violations are sparse. You know, if there's going to be violations, and by the way, the L1 norm should be the right thing here because it says, you know, it's got a V. I mean, we'll see it's not quite an L1 norm, but it's exactly this. Actually, it is an L1 norm for something that's positive. You know, it's something, it means what you want is something that keeps up the pressure to drive you to zero. But if you have to violate, it shouldn't go nuts. And it should not be a function, a penalty that grows. It should grow linearly. Okay? Okay, so that's the idea. So in fact, that leads you immediately to the following. Let me do it this, I'll write it another way. I'll write AI transpose x plus b. I want that to be bigger than 1. Okay? So I want this thing to be bigger than 0. That's what I want. Now I know that I actually can't choose an A and a B. Well, that one and the other ones, so that all these inequalities hold. Everybody following this? So I want that. If that's positive, I'm totally happy. Right? So you might do something like this. You might form AI transpose x plus b minus 1, the minus part. Okay? If you satisfy that inequality, there's no bill here. You don't pay anything, right? But if this thing becomes negative, then you start paying. And you pay linearly. So what function is that? That's a function that looks like this, right? Looks like that, right? And this is called the margin in the inequality. And what this says, if your margin's positive, no charge whatsoever. If it's negative, you charge linearly for negative margins, right? Everybody sort of following this? Okay. Now, when you look at that, and by the way, it helps to turn your head about 40 degrees, then L1, your L1 part of your brain will light up. Okay? I mean, it's the same thing, right? Okay? So, and by the way, this is called hinge loss, is the name for this in several fields. I think that in both in modern statistics and in machine learning is called hinge loss. Anyway, so that's hinge loss. And so it suggests that actually doing something like this, adding that in would be a great idea because, I mean, it doesn't look like L1, but by the time you see this, I mean, it should evoke, L1 is not to be taken literally, although a lot of people do. This is L1, right? Actually, it's linear plus L1, so it actually kind of is. But you look at that, and sparsity, the sparsity part of your brain should be lighting up, okay? Right? And what does it mean that if this is sparse? It's super cool. If that's sparse, it says the following. It says that you satisfy most. It means that misclassifications, these are not, by the way, misclassifications. There's even a little extra there because the one, without the one, it's misclassification, right? This says that misclassifications are sparse. That's exactly what you want. Everybody following this? I mean, that was a very long story, but the idea is, I mean, I just wanted to give the whole, like, everything about what you're doing here. Okay, so that's what this is. U is a slack variable here. I mean, this is the traditional description of it. Actually, this is a more modern description. You don't even introduce U's. Because you just look at it, you say it's convex, done. Right? That's the correct way to do it, in my opinion. But we'll do it the traditional way. The traditional way is you say, I would like to satisfy this inequality and this one. It's determined that you cannot. And then you go, oh, okay, fine. Then you add in slacks. Now, the slacks are, by the way, nothing but these things, right? So a slack is something, it says, fine, I'll subtract something from the 1 to make it easier to satisfy this, and I'll do the same here. I'll make the inequality easier. These are the U's and V's. Those are pos. And then I'll minimize those. And by the way, you'll find out this problem is absolutely identical to the problem of this, plus, of course, the opposite ones for the Y's, right? So you get exactly the same problem. Okay, everybody following this? Okay, so that, and you should even think of this. It's a beautiful thing. You should think of this thing as the L1 type heuristic for solving the following hard combinatorial problem. Find me a hyperplane that satisfies as many, that misclassifies as few as possible, right? So that's the correct interpretation of this. Okay? And you get something like that. Here's a case. Okay. Now, the only thing you have to do now is you put the two together and you have something kind of famous, right? So, and I guess the traditional one would look something like that, right? So, but you get the same trade-off curve. So what you do now is this: you put slacks in to minimize for actually misclassifying, right? And then at the same time, you can also think of this as regularization, by the way. So here, traditional L2 regularization turns out to have a beautiful geometric interpretation because when you're minimizing the norm of A, I guess you call it the weight vector or something like that. If you're minimizing the norm of the weight vector, it turns out that's equivalent to, if you go geometrically, to saying don't look for a hyperplane, look for a slab. And in fact, maximize the width of the slab, which means that you've separated them well. Everybody kind of seeing all these things go together? So, I mean, for people who've seen this before, that's fine. You may not have seen the full geometric interpretations, but now you have. So it's actually kind of cool. So this is given the name support vector machine. Here you have a parameter, and the parameter is very simple. It trades off the parameter, and I'll describe it geometrically. And there are statistical interpretations of all of these. I'm not going to go into them, but there are. So the geometric interpretation is quite beautiful. Lambda, or gamma here, sorry, trades off the width of the slab, and this is going to be very rough, the number of inequality violations. Okay, and that's what it does, right? And so you can imagine what turning that parameter will do here. This is unbelievably widely used. I mean, not as much as least squares or something like that, but it's catching up. Let me put it that way. So it's used tons of places, everywhere, all the time, right? So you couldn't possibly get through a day here, except if you're like hiking in Yosemite or something, and maybe even then you couldn't. When something you didn't run through a support vector classifier. I mean, you'd have to touch no electronics, and I don't know what else you'd have to do. So, but be very hard to do anything. Certainly don't pick up your phone or anything like. Don't read email because then it's all over. So anyway, so yeah, these are good things to know. Okay. Let's look at the idea of nonlinear discrimination. So here, we've been looking at linear discrimination. We can just as well look at nonlinear discrimination because, in fact, it turned out that the fact that the classifier was linear was totally irrelevant. All that mattered was that it was linear in the parameters, right? So nonlinear classification says, find me a function f that is, positive on the x's, negative on the y's. Okay? So here's one approach to it. Actually, there's multiple approaches here. I mean, one which doesn't fit in this theme, but we could talk about, but don't have time to, would be sort of kernel methods. But we're not. Instead, we're going to look at something that's just much simpler and that fits with the theme of convex optimization. What you do is you simply take a set of basis functions here, and what you're going to do is you're going to look at a finite dimensional set of candidate functions. That's all. And these are basis functions, right? F1 through Fk, right? They could be anything you like. So it could be polynomials. They could be weird exponentials. They could be things that pertain to your particular problem, right? I don't know why, but I mean, could be. These could be prolate spheroids or something like that, or Bessel functions of some order. I mean, I don't know. They could be anything, right? These could be the eigenfunctions of some partial differential operator, right? Doesn't matter, right? It's just supposed to be functions you're going to linearly combine to do separation. Okay. So here it's the same thing. You just end up with it. I mean, absolutely nothing whatsoever is different. I mean, nothing, right? So that's what you get. And so this tells you can do fun things like this. You could say, please separate my points quadratically, okay? And that says, find me a quadratic function. That's a general quadratic function. And what's being asked is that you should find P, Q, and R. Those are the variables that separates your points. Okay, so here's an example of quadratically separable points, right? And this, by the way, goes back to our question of what would you do with those ellipsoids. This would be if you had two types of data. You had places where, let's say, a pilot flown and came back. Let's suppose that's the things inside. And these are the ones where there was no recovery. That's a little bit gruesome, sorry. Okay, so something else, but that's the idea. Okay? And so this would be the case. It's a linear program to compute actually just quadratically separation. Now, quadratic separation by itself does not require, there's no curvature constraint, right? So in fact, in this case, you might as well, you could, if you just do straight quadratic classification, you could actually be looking for a hyperbola that separates them. Everybody following this, right? And if, depending on what your data is, that could be completely reasonable and interesting. Everybody got this? If you want to insist that, for example, if you say, find me an ellipsoid that covers these points, but not those, then you simply add a constraint that says that the P is less than or equal to, actually, you would add P negative definite, for example, to get an ellipsoid, or the exterior of an ellipsoid would be P positive definite. That's homogeneous, and that translates to this. Okay, and now you have an SDP. Everybody following this? So this is the idea. I mean, here's a quasi-convex problem. It says here's two sets of points, and this says please separate them by the minimum degree polynomial in R2. Everybody got that? And without even saying anything, you should understand that that is quasi-convex. Why? In fact, how was that done? How was that figure done? You take the two sets of points, and what's the first thing you try to do? You first try to separate them by linear, and you can't, okay? Because we're looking at the data. You cannot, okay? And that doesn't work. So now you try quadratic, and you cannot, okay? Then you try cubic, and you can't. And then you try quartic, and you can. Everybody, so that's the idea, right? So, I mean, I don't know why you'd want to. And by the way, now, I mean, one of the nice things about these sort of convex formulations is, we're showing you the simple ones, but in fact, you can just, it's like cooking. You can add stuff in and things like that. I mean, for example, here, suppose instead you want to say, this is what I want to do. I really want to do that. But you know what? It doesn't work exactly, and I don't mind if a few end up misclassified. Everybody following this? So what would you do? Yeah, you had the U and the V, the slacks or whatever you like, and then and then you have a parameter that would trade off various things, right? I mean, so that's exactly what you do. You add in U and V, and then you'd end up computing an ellipsoid, and there would be, if you're lucky, a couple of points outside, a couple of points on either side of the boundary that went the wrong way. Everybody got this? So it's okay. So I mean, you get it.